This is William Michael of the Classical Liberal Arts Academy, and in this video I'd like to continue walking with students through the study of this section 1.2 in elementary algebra. This section of the text is very rich. There's a lot of information included in this section, and I really want to make sure that students who need help get that help that they need by walking through this slowly and making sure that everything is clear. In a first video, we worked through this first objective, which is to use variables and algebraic symbols. And because that's often a topic that students struggle to get over as they get into algebra, I took my time and we walked through that first part of the section, and I think that that was pretty clear. We got into simplifying expressions a little bit, but we're going to pick up in this video with simplifying expressions using the order of operations, and we'll try to get through as many of these other objectives as we can, just moving forward carefully and making sure we read everything and everything is clear before we move forward. So we're going to scroll down to where we left off at the beginning of the last video and continue our study of section 1.2 on the use of on using the language of algebra. So here's where we left off at the end of that first video, and we can see that this section is titled Simplifying Expressions Using the Order of Operations. Simplifying Expressions using the order of operations. Now, we looked at simplifying expressions in the previous lesson. If we go back up here a little bit, I guess it was further down here actually. This last set of, here we go. It says simplify 3 to the 4th power. We talked about simplifying. Now you may wonder, why are we calling this simplification when really all we're doing is writing an answer that's equivalent to this? It's not a very clear example, and it leaves us with that question. But what we need to understand is that in algebra, we can't always find a solution like this. So sometimes we'll have an expression that we can take a few steps to make things simpler in the expression, but we can't simplify it all the way down to coming up with a number that's equivalent to what's given in the expression. So this is an overly simplified example. And in arithmetic, we might say solve or find the answer that is equivalent to 3 to the 4th power. We might use words like solve, find the answer, and so on. But in algebra, what we're normally doing is simplifying. We're taking an expression and we're asking, how can we use what we know about numbers, what we know about the operations, what we know about algebra? So how can we use what we know to express this expression in simpler terms? So normally we're challenged to simplify an expression, and we're going to actually get into that here in this video. So we see our goal here is to simplify expressions in algebra using the order of operations. And we have here in bold what it means to simplify an expression, which is important. This is a very important concept in algebra, so if you're taking notes, I recommend you jot this down and make sure that you understand what this phrase means, what it means to simplify an expression in algebra. To simplify an expression means to do all the math that is possible. To do all the math that is possible. For example, to simplify 4 times 2 plus 1, 4 times 2 plus 1, we'd first multiply 4 times 2. So we look at this and we say, well, we can multiply 4 times 2. That's something that we can do. So we multiply 4 times 2. We get 8. So now we have 8 plus 1. And then we add the 1 to get 9. and we can write something that looks like this. We start with this expression, which is not as simple as it could be, because there's some math that we can do on this expression. We can multiply 4 times 2 and get 8, and then add the 1. And we can find that this expression here is actually equivalent to 9. And that is simplifying that expression, because, again, what it means to simplify an expression is to do all the math that is possible. In some examples, in many examples, in fact, you'll see that we get to a point where there's nothing else we can do. We've done all the math that's possible, and we're just left with an expression that's as simple as it can get. And that's what it means to simplify an expression. By not using an equal sign when you simplify an expression, you may avoid confusing expressions with equations. So you see here how they write this out, but they don't use an equal sign. They don't write 4 times 2 plus 1 is equivalent to 8 plus 1. They don't write equals 9, because they don't want this to appear as an equation. They want to show that we're simply simplifying this equation. But the problem, as I said, is normally when we're simplifying an equation, we're not coming down to an actual numerical answer. We're usually getting to a point where there's nothing more that we can do, and that is the simplified expression. So we'll see that in coming parts of either this lesson or future lessons. To simplify an expression is to do all the operations that can be done in the expression, to do all the operations in the expression. Now, you can also assume that when we say do all the operations in the expression, or do all the math that can be done, obviously a student who's not very good at math and doesn't understand the principles and operations of mathematics is not going to be able to determine when more math can be done, whereas a more skillful math student may be able to look at an equation and say, oh, there's still more we can do. We can simplify this further. So our ability to simplify expressions depends on our expertise in mathematics. So as we grow in our understanding of mathematics, we'll be able to simplify more effectively as we move forward. Let's keep reading here. We've introduced most of the symbols and notation used in algebra, but now we need to clarify the order of operations. The order of operations. Otherwise, expressions may have different meanings, and they may result in different values. For example, consider the expression here, 4 plus 3 times 7. 4 plus 3 times 7. And notice the question is, where do we begin? Because we're asking about the order of operations. So we can see that there are two operations marked here with symbols. We can see addition over here, and we can see multiplication over here. But is there a certain order that we're supposed to work in, or can we work in any order? That's the question of order of operations. So we've got to understand this before we can know what to do with an expression like this. So let's look at how this textbook explains the order of operations. If you simplify this expression, what do you get? If you simplify this expression, what do you get? Some students may say that they get 49. When they simplify this, they may say, oh, I did it and I got 49. Well, how do they come up with 49? They start with the expression 4 plus 3 times 7. And what they do is they add 4 plus 3. So they start at the left like they're just reading a sentence. And they start by saying 4 plus 3, and then they say, well, that makes 7. And then they add the multiplication times 7, and they say, okay, I've got 7 times 7. That gives us 49. So they say this expression can be simplified by writing 49. But other students say, no, that's not right. I got a different answer. Others will take 4 plus 3 times 7 and say, well, we multiplied this first. So we took 4 plus the product of 3 times 7, which is 21. And 4 plus 21 makes 25. So these students, by working from left to right, came up with 49. These students, starting with multiplication, came up with 25. They came up with two different answers. So what's the problem here, and how can we avoid this trouble? The answer to this is we have to understand that there is an order of operations. There is a right way to do the math in this expression and a wrong way to do the math. And we've got to learn what the right order is to do the math or to do the operations in this expression. Imagine the confusion in our banking system if every problem had several different correct answers. And note that these are not both correct answers. The same expression should always give the same result. So mathematicians established some guidelines that are called the order of operations. So here we're going to learn the rules for how to perform the order of operations. And this is very important. You can see this is the difference between getting a wrong answer and a right answer. And this can be the solution to some great confusion, especially when the expressions get more complicated, as we'll see later on. So to perform the order of operations, step 1, if there are parentheses and other grouping symbols in the expression, we should take care of them first. Simplify all expressions inside parentheses or other grouping symbols like brackets and braces, working on the innermost parentheses first. So we should always start with the innermost grouping symbols or parentheses. Start there. Do those first. Step 2, simplify all expressions with exponents. Step 3, multiplication and division. Perform all multiplication and division in order from left to right. Notice it doesn't say perform all operations from left to right. It says perform multiplication and division from left to right. And then lastly, perform all addition and subtraction in order from left to right. So we start with anything in parentheses, then exponents, then multiplication and division, then addition and subtraction. And so we can kind of see a pattern here. We can see that the last step would be the simplest operations, addition and subtraction. Then the more complex operations, multiplication and division. Then some more complex operations working with exponents. And then lastly, the most complex, which is working with different levels of groups and symbols in parentheses, brackets, and braces. So we can see there's some order, some reason here, working from the most complex down to the simplest. But I would like to give you another quick explanation before we move on here. I'd like to explain what's going on here. If we follow this rule for the order of operations, 4 plus 3 times 7, we would start at step 3. There are no parentheses or grouping symbols. There are no exponents. So we would start at step 3, looking at multiplication and division. So we would ignore the 4 and the addition here and move to the multiplication, 3 times 7. We would do that first, and we'd get 21. So this second example here is actually the right answer. This example follows the order of operations. 25 is correct. 49 is wrong because they did addition first. But here's what's actually going on here. This expression is made up of two algebraic terms. Algebraic terms are expressions separated by addition or subtraction. So when we see an addition sign in an algebraic expression, that separates two expressions or terms. So we have 4 as one term, and we have 3 times 7 as another term, and they're separated by addition or subtraction. So this is an expression with two terms. 4 is a term, and 3 times 7 is a term. So what we're actually doing is simplifying this term first by multiplying and getting 21, and then we're adding the two terms. So there actually is reasoning behind this order of operations. It's not explained here, but it has to do with identifying the terms or the parts of an expression, and the parts are separated by addition and subtraction symbols, okay? That's the real way to know how to do this. But this is a good guide, and they give us this helpful little mnemonic device or way of remembering the order. Students often ask, how can I remember this order? How will I remember this? There's a way to help you remember. Take the first letter of each word and substitute the silly phrase, please excuse my dear Aunt Sally. Please excuse my dear Aunt Sally. And so you can see the P from parentheses, the E from exponents, the M and D from multiplication and division, the A and the S from addition and subtraction. If we take those first letters and substitute this silly expression, please excuse my dear Aunt Sally, that may be a way that helps you to remember the order of operations. My advice is just memorize this. It's not that difficult. Parentheses, exponents, multiplication, division, addition, subtraction. It's not that complicated. You may find something like this helpful. I tend to think that this is pretty silly. So anyway, order of operations explains for us how to attack an expression like this and know what to do. So I hope that's helpful. This was, as I said, the wrong answer. This was actually the right solution. Let's keep moving here. It's good that my dear goes together, as this reminds us that multiplication and division have equal priority. We do not always do multiplication before division or always do division before multiplication. We do them in the order from left to right. Similarly, Aunt Sally goes together, so it reminds us that addition and subtraction also have equal priority, and we do them in order from left to right. So if we're left with a number of multiplication and divisions to be taken care of in an expression, we just move from left to right in the expression. There's no one that is more important than the other or one comes before the other. We just move from left to right in the expression. And the same is true in addition and subtraction. Addition is not more important than subtraction, doesn't come first. We just move from left to right, and whatever happens to come first is what we take care of. All right? So it's showing us here that if we do remember this silly phrase, the my dear being together, helps us to remember that multiplication and division are equal, and the Aunt Sally being together remind us that addition and subtraction are equal in priority. I hope that makes sense. All right, so we're given a couple problems here to look at, and we're asked to simplify these expressions. So let's take a look. We have 4 plus 3 times 7, which we already saw above. And looking at this, we see that there's no parentheses, there's no brackets or braces, there's no exponents, so we don't have anything to do there. The next thing in the order of operations is multiplication and division. And as we look, we find one multiplication here, 3 times 7. So we're going to do that first. And we see that down here at this step, 4 plus 3 times 7 gives us these two terms, 4 plus 21. And we can add them together and get 25, which is all the math that can be done with this expression. So we use the order of operations to simplify that expression. Now, if we look at the second example, this gets a little more difficult. Notice we've got parentheses that enclose 4 plus 3. So they're showing us that if we take these numbers and write them in the same way, 4 plus 3 times 7, but in this example, the 4 plus 3, the addition was actually in parentheses, we would simplify this expression differently because of the parentheses, because the order of operations starts with parentheses. So we would actually solve what's inside the parentheses, or simplify what's inside the parentheses first. And we can see that down here. Are there any parentheses? Yes, there are. There are parentheses around 4 plus 3. So we're going to solve that addition first. And you can see we have 4 plus 3 makes 7 in parentheses. Are there any exponents? No. So we don't have anything to do there. And all we're left with is a multiplication. So we multiply 7 times 7 and get 49. So notice, if we wanted to add these two numbers first, we could note that that should be done by putting them in parentheses. That would make that addition come first. But if we leave those parentheses off like this, that would actually tell us that we should multiply first and then add 4. So you can see how we can communicate different expressions by using parentheses or by choosing to not use parentheses. It's as if the sentence changes in meaning because there are no parentheses. So that's showing us the importance of parentheses and how they affect the results in mathematics. All right, let's look at a couple examples. We're shown here 12 minus 5 times 2. There are no parentheses. There are no exponents. So then we look to multiplication and division. We multiply 5 times 2 and get 10. We subtract that from 12, and we're left with 2. In letter B, we have 12 minus 5 times 2, but 12 minus 5 is in parentheses. So step 1, we deal with parentheses. We subtract 5 from 12 and get 7, and then multiply 7 times 2 to get 14. So these two expressions look alike, but the parentheses tell us to work through them differently, and it leads us to two different solutions. The same thing would be true down here with this one. I'll skip this. You could do this on your own. Let's look at a more complicated problem. Here we're given an expression that's more complicated, that's going to challenge us to think about the order of operations. 18 divided by 6 plus 4 multiplied by 5 minus 2. 18 divided by 6 plus 4 multiplied by 5 minus 2. And if you wonder, well, why did you say multiplied by here? Because remember, we learned that one way to express multiplication was to simply write the variables next to each other, like a, b. That's what's being done here. We have 4 written next to this term, 5 minus 2. So it's like two variables or two quantities written side by side, which is a way of showing multiplication in algebra. So if we look at this, we have to ask, what's the first thing we should do? What is the right order of operations? We've got division, we've got addition, we've got multiplication, and we've got subtraction, all 4 of the basic operations in this expression. How can we simplify? What do we do first? Well, the order of operations tells us that we should take care of parentheses first. And so we've got a part of this expression here inside parentheses, so we're going to take care of this and simplify this first. 5 minus 2 makes 3. So we've got 18 divided by 6 plus 4 times 3. Now, we've got a division and a multiplication left. There are no exponents, so we can skip that step, but then we're asked, is there any multiplication or division? And the answer is yes. We have both division and multiplication. So which should we do first? Well, the rule told us that multiplication and division are equal in priority. So there's no one that should come first. What we were told in the rule was to simply start at the left and work to the right. So what we're going to do is start with 18 divided by 6. 18 divided by 6. So we've solved inside the parentheses and found that that is equal to 3. And let me ask you, in this expression, this is something modern algebra books don't teach very well. In this expression, how many terms are there? How many parts are there in this expression? 18 divided by 6 plus 4 times 3. How many parts are there in this expression? The answer is 2. Before I explained that an expression separates terms by addition and subtraction. So we see that 18 divided by 6 is one term. 4 times 3 is another term, and those two terms are separated by addition. So there are two terms, and that's what we're going to solve. We're going to simplify the first term, and then we're going to simplify the second term and save addition and subtraction for last. So let's do this first. 18 divided by 6 gives us 3. We see that down here. So we're then left with the expression 3 plus 4 times 3. We still have a multiplication, so we're going to take care of that first. So we have 3 plus 12, which is equal to 4 times 3. And we ask, is there any more math we can do here? And the answer is yes, we can add. So we add 3 plus 12, and we have 15. So 15 is the simplification of this complex expression, 18 divided by 6 plus 4 times 5 minus 2. The order of operations tells us how to approach this problem and come up with the right answer. Let's try another one. Down here we get more complicated. Now there are more examples that you can work on by yourself if you'd like to test your understanding. And if you have trouble with any of this, just let me know, and I'd be happy to walk you through more of these exercises. But you're in control of the video here, so you can pause it and work on these if you want, while I go ahead and move on in the video to the next example. So let's look at a more complicated expression here. Look at this messy thing. We have 5 plus 2 to the third power plus 3 times, and then we've got this whole term set in brackets here, 6 minus 3 times 4 minus 2 in parentheses. So we've got quite a complicated expression here, but thankfully the order of operations makes this very simple. We just move one step at a time through the order of operations. So if we look at this and we're told to simplify it, we have to ask, how can I simplify it? Where should I begin? And the order of operations tells us to start with parentheses. And it says to start with the innermost parentheses because we have two different sets of grouping symbols here. We've got parentheses, 4 minus 2, and then we've got these brackets which contain this entire expression here. So the rule tells us to start with parentheses and grouping symbols and work from the innermost group first. That would be this parenthesis here. So we see inside this innermost parenthesis, we have 4 minus 2. So we would solve that first, which is equal to 2. And we can see that right here. We see 5 plus 2 to the third power plus 3 times 6 minus 3 times 4 minus 2. We simplify that parenthesis first and write 3 times 2. We then look at this again and we ask, okay, what's next? What's the next thing we should do? Well, the next thing would be, again, to work with groups. And since we've got brackets here, we should take care of these brackets next. So starting inside this bracket, we now apply the order of operation. We have 6 minus 3 times 2. What should we do first inside these brackets? Well, we should do multiplication first, not subtraction. We should do multiplication. So we're going to multiply 3 times 2. That leaves us with 6 minus 6 inside the brackets. So we now have 3 times 6 minus 6. And again, we're going to solve what's inside the grouping symbols. So we're going to subtract 6 from 6. That leaves us with 0. So now we have 5 plus 2 to the third power plus 3 times 0. The order of operations would then tell us that since we have no more groups, these brackets are here just to show us that there was an expression inside those brackets, but now we've already simplified that as far as possible. So when we look at this, there's no more groups here to deal with. And so we move on to the next step in the order of operations, and that's exponents. And we ask, are there any exponents in this expression? And the answer here is yes. We have 2 to the third power. 2 to the third power, so we need to simplify that first. 2 to the third power means 2 multiplied 3 times. So we have 2 times 2 times 2, and that's equal to 8. 2 times 2 is 4. 4 times 2 is 8. So we take care of that exponent first. We simplify that to 8, and we're left with 5 plus 8 plus 3 times 0. Now we look at this and we ask, are there any groups? No, there's no groups. Are there any exponents? No, there's no exponents. So what's next in the order of operations? What's next would be multiplication. So 5 plus 8 plus 3 times 0. So we're going to do this multiplication next. 3 times 0 is 0. So we have 5 plus 8 plus 0, as we see here. Now we look at our expression and we ask, are there any groups? No. Are there any exponents? No. Is there any multiplication or division? No. All we've got is addition and subtraction. And we're told in our rule to just start at the left and move from left to right. So we're going to take 5 plus 8, and 5 plus 8 makes 13 plus 0. 13 plus 0 makes 13. So 13 is the answer to this problem where we're asked to simplify this complicated expression. And now I know, again, that may be challenging because I moved through it pretty quickly, but the reason I'm moving through it pretty quickly is because this is a video. You can pause it, you can rewind it, you can watch that again and again and make sure you understand everything. Okay? So don't feel upset if you feel like we moved through that pretty quickly. You're in control of the video. Just hit pause, back up, and watch it again. Take your time. You can even change the speed that the video plays if you're watching on YouTube. I'm not sure about Vimeo, but sometimes you can even change the speed of the video and just slow it down. So you may want to look at doing that. But you're in control of that. So I'll leave you to go over that by yourself. And if you just can't understand it and don't know what's going on, then what I recommend is you get in touch and let me know that you need some more help. And we can set up a time to chat and just walk through a problem together, all right? You've got 2 more exercises here to practice, which you can work through and see if you can find the right solution, okay? Let's move on now to the next section. So we looked at simplifying expressions using the order of operations. We looked at simplifying expressions using the order of operations. You should know what it means to simplify an expression. It means to do all the math that we can. And you should know what the order of operations is. You should know that there's a certain order that we should follow when we do all the math to simplify an expression. So that's the previous part of this section. Now we're going to move on to another part, which is to evaluate an expression. To evaluate an expression. In the last few examples, we simplified expressions using the order of operations. Now we'll evaluate some expressions, again, following the order of operations. To evaluate an expression means to find the value of the expression. So this word evaluate, which is a new word here, realize that it just means to find the value. To evaluate an expression means to find the value of the expression. To evaluate an expression means to find the value of the expression when the variable is replaced by a given number. So we're going to take a variable in an expression and actually replace it with a given number. So we're going to give a specific number value to a variable and then simplify the expression and find the value of that expression when that variable has that given value. Okay? Here we have the definition of the term evaluate an expression in the gray box here. To evaluate an expression means to find the value of the expression when the variable is replaced by a given or known number. All right? To evaluate an expression means to find the value of the expression when the variable is replaced by a given number. And we'll see what this means by looking at some examples. This is actually quite simple. To evaluate an expression, substitute the number for the variable in the expression and then simplify the expression. To evaluate an expression, substitute that number for the variable in the expression and then simplify the expression. So let's take a look. Evaluate the expression 7x minus 4. So 7 times x minus 4. Evaluate this expression. Find the value of this expression when x is equal to 5. So all we're going to do to evaluate this expression is replace x, which is the variable. We're going to replace the x with the number 5. And then we're going to simplify that expression. So what we're going to have is 7 times 5 minus 4. 7 times 5 minus 4. We see that written down here. So 7x minus 4 is our expression. We're going to substitute x with 5. So that gives us 7 times x, or 7 times 5, minus 4. So we have this expression now, and we use the order of operations to simplify it. There are no groups, even though we have parentheses drawn here. It's just to separate the 7 and the 5, so it doesn't look like 75. But we have 7 times 5. There's no groups. There are no exponents. So we come down to multiplication, and we have one multiplication, 7 times 5. We find the product of 7 times 5, which is 35. And so we rewrite, we simplify the solution and write 35 minus 4. And then seeing that all we have left is a subtraction, we simplify that by performing that operation. 35 minus 4 leaves 31. So the value of this expression when x equals 5 is 31. That's what it means to evaluate an expression, to find the value of an expression in a particular circumstance where one of the variables is actually known. And we've done that. So we walked through that and found that the value of the expression is 31 when x equals 5. Now, letter B here asks us to find the value of this expression when x equals 1. So now we're going to substitute 1 for the variable x. So 7x minus 4 when x equals 1. That gives us 7 times 1 minus 4. The order of operations tells us to solve the multiplication first. So we have 7 times 1 makes 7 minus 4. And then to solve the subtraction last, 7 minus 4 leaves 3. So the value of the expression when x equals 5 is 31. And the value of the same expression when x equals 1 is 3. So we can evaluate the expression with two different numbers substituted for the variable. I think that's pretty simple. If you just walk through that again or read through it on your own, I think you'll find it's pretty simple. But you've got some more problems down here to practice and work with that you can check out and test yourself to make sure you understand things. And again, if you have any trouble, have any questions, if this isn't clear, just get in touch with me. we can meet on live chat and walk through exercises together, okay? Let's keep moving here. We have another exercise, or another example, where we're asked to evaluate the following expressions when x equals 4. So we're given the value of a variable here. We're told that x is going to be equal to 4, and we're given two different expressions. So this is written a little differently. Here we're given two different expressions with one value, and we're asked to take x equals 4 and find the value of x squared. And then we're asked to find the value of 3 to the x power, or 3 to the 4th power, since x equals 4. So let's start with x squared. We write the expression x squared, and then we substitute the known number 4 for the variable. So we rewrite it as 4 squared. We then think about order of operations, which tells us to do exponents. So we solve this by multiplying 4 twice. We get 4 times 4, and that leaves us with 16. And there's no more math that we can do, so that's the end of our simplification. So when x equals 4, the value of the expression x squared is 16. Now we're asked to perform another, or evaluate another expression, 3 to the x power when x equals 4. So we write the expression 3 to the x power, and then we replace x with the known variable 4. 3 to the 4th power, which means we're multiplying 3 4 times. So we write that out here, 3 times 3 times 3 times 3. 3 times 3 is 9. 9 times 3 is 27. 27 times 3 makes 81, and that's written here. So 81 is the value of 3 to the x power when x equals 4. 16 is the value of the expression x squared when x equals 4. So again, this is evaluating expressions when we replace a variable with a known quantity. All right? Pretty simple, but again, you've got some more practice exercise here that you can work on. Let's move down to another example, and you can see that things get more complicated. It gets more complicated. Evaluate the expression 2x squared plus 3x plus 8 when x equals 4. Now notice x is actually used in this expression twice. 2x squared plus 3x plus 8 when x equals 4. So we're going to substitute 4 in for x in two different places. So let's see how that gets done. We write out the expression 2x squared plus 3x plus 8, and then we substitute 4 for x. So we have 2x squared, which is 2 times 4 squared, plus 3 times 4 plus 8. 2 times 4 squared, we solve the exponent first, following the order of operations. So we see 2 times 16. We then have simply substituted x with 4, so we have 3 times 4, and then we have the addition of 8. So 2 times 16 plus 3 times 4 plus 8. When we look at this expression, we see that we've got two different operations. We've got multiplication and we've got addition, and we do multiplication first. So 2 times 16 gives us 32. 3 times 4 gives us 12. Now we're just left with two additions. We start on the left and do the first addition first. 32 plus 18 makes 44. 44 plus 8 makes 52. And here we see the answer. That expression simplified as far as possible when we know that x equals 4. The value is 52. All right, so even if the expressions look more complicated, don't look at the expression and get nervous or confused, just write the expression and then begin thinking about the order of operations. The order of operations is what allows you to take the expression apart, work on it one step at a time, and keep everything simple. All right? The order of operations helps you to know how to get to work on what appears to be a complicated expression. Evaluating expressions is not very difficult. It's quite easy as long as you know how to do the operations and you follow the order of operations. If you work through one of these problems and come out with a different answer, and you're sure that all of your calculations were correct, but you come out with a different answer, the problem is usually that you did not follow the order of operations. So that could be the cause of your coming up with a different answer, okay? There's a couple more examples down here that you can practice with to make sure you understand and feel comfortable. And if you need any help, just let me know. Let's keep moving here. Identifying and combining like terms. Remember, our goal is to simplify expressions. To simplify expressions. So if an expression has terms in it that are similar, they're like each other, they can usually be combined to simplify the expression, okay? So we want to learn how to identify like terms and then how to combine like terms, all right? How to identify and combine like terms. Like means similar, terms that are like one another, terms that are similar, they have something in common. Algebraic expressions are made up of terms. And I mentioned this word before. I mentioned terms when we talked about order of operations. Algebraic expressions are made up of terms. A term is a constant or the product of a constant and one or more variables. A term is a constant or the product of a constant and one or more variables. And we've got that definition written here. And that's kind of difficult to listen to and think about. A term is a constant or the product of a constant multiplied by one or more variables. So in both cases, a term is a product. It's either the product, it's a constant or a product. It's either a constant or the product of a constant and one or more variables, all right? So examples of terms are listed here, and we can see that some of them can be simple, like the number 7 or the letter y. Some of them can be more complicated, like 5 times x squared. Here we have 9a, and here we have b to the 5th power. Each one of these quantities separated by commas, each one of them is a term. Each one of them is a term. Here we can see the number 7, which is a constant, right? It's a known number. Here we can see y. Here we see 5x squared. The exponent is really just a product. We have x multiplied by itself multiplied by 5. Here we have 9 multiplied by a variable, and here we have a variable b multiplied 5 times. So we see a term is a constant or the product of a constant and one or more variables. Now, what you'll see here, what I want you to see, is we're learning the definition of a term, but the definition of the term is assuming that you already know what a constant is. This definition assumes that you already know what a product is. It assumes that you already know what variables are. So you can see how the knowledge in algebra builds on itself. So if you don't learn carefully the first lessons, if you didn't learn what a constant is, if you don't know what a product is, if you didn't learn what a variable is, you really can't understand this definition. And that's why when you come to a definition like this and you read it, and you say a term is a constant or the product of a constant and one or more variables, and you You say, I don't understand that. Mr. Michael, I don't get it. I don't know what this means. The reason why is because you don't know the meaning of these words. So you're going to have to go back and review what a constant is. You're going to have to go back and review what a product is. You're going to have to go back and review what variables are. And then when you get the meaning of those words clear in your head, you can come back and now read the definition of a term and say, oh, okay, I understand now. A constant is a quantity that doesn't change. A product is the result of multiplication. And a variable is a quantity that can change. So if I look at 7, that's a constant. So a term is a constant. So 7 is a constant. It's a term. Y is a variable. Y is a variable. 5 times x squared is the product of a constant multiplied by a variable multiplied by itself. 9a is the product of a constant and a variable. B to the 5th power is the product of a variable multiplied 5 times. So if you don't understand a definition, you probably need to go back and study the meaning of the words that are used in the definition, and then return to study the definition, okay? So we learn what a term is here, and we're given some examples of terms. We then learn the constant that multiplies the variable is called the coefficient. The constant that multiplies the variable is called the coefficient. So if we have 9 times a here, 9a, 9 is a constant, a is a variable, 9 is called the coefficient. 9 is called the coefficient. If we see 5 times x squared, and x is a variable, 5 is a constant, and x is the variable, 5 is a coefficient of x, x squared. 9 is the coefficient of a. The coefficient of a term is the constant that multiplies the variable in a term. And just so you know, this word coefficient may be distracting because it's some fancy new word. The word efficient means something that makes something. It's a factor. A factor is what makes a product. So in 2 times 4 equals 8, 2 and 4 are called factors, and 8 is called a product. It's the product that's made by the factors or the makers of the product. If we were to look at the 2 factors and just call them cofactors, that would really express the idea of a coefficient. A coefficient is really a cofactor, one of a number of factors. All right? Think of the coefficient as the number in front of the variable. The coefficient of the term 3x, or 3 times x, is 3. When we write x by itself, the coefficient is 1 because x is equal to 1 times x. So any variable written by itself, like x here, has a coefficient of 1. The simple lesson is that the coefficient is a number in front of a variable, or a number that is multiplied by a variable in an expression. Okay, so 2 definitions here, term and coefficient. So we're given a few examples to identify the coefficient of each term. Identify the coefficient. The coefficient is simply the number in front of the variable. It's the constant that multiplies the variable. So for letter A, we have 14y, which is equal to 14 times y. So we have a product here, and we've got 2 factors, the number 14, or the constant 14, and y. And we're told that the coefficient of a term is the constant that multiplies the variable. The constant that multiplies the variable y is 14. So the coefficient of 14y is 14. The coefficient of 15x squared, again, would be 15. It's the constant that's multiplied by the exponent. And then lastly, letter C, we just have the letter A. We're asked to identify the coefficient. It says the coefficient is the number in front of the variable. We look at the letter A and we say there's no number in front of the variable. So what's going on here? Is it right to say there's no coefficient here in letter C? And the answer is no, that's not right. We were told here that when we write x, when we write a variable by itself, the coefficient is understood to be 1 because x is equal to 1 times x. So anytime we see a variable by itself, it's the same thing as writing 1 times the variable. So the coefficient of A would be 1, all right? And they give you a few more examples here to work on to make sure this is clear, and there's a few more examples down here to work on. So plenty of opportunity to test yourself. Next up, some terms share common traits. Look at the following 6 terms. Which ones seem to have traits in common? So some terms share common traits. Remember before we talked about like terms. We see that we're working towards the definition of like terms here. So when we look at a list of different terms, we're asked, do any of these have anything in common? Do they have any common traits? So we look at 5x and 3x, for example, and we could say, yeah, 5x and 3x are similar. Both of them are terms that have a constant and the variable x. Here we have the constant 5 and the variable x. Here we have the constant 3 and the variable x. So they're similar. Here also we have n squared, and then here we have 9 times n squared. So we have the coefficient 9 multiplied by n squared, and here we have n squared, which is really 1 times n squared. So we have 1 times n squared, and we have 9 squared. And then we've got 2 constants, 7 and 4. So we can see some similarities between 5x and 3x, between n squared and 9n squared, and between 7 and 4. Our lesson says 7 and 4 are both constant terms. And we said that when we looked at it. 7 and 4 are constants. 5x and 3x are both terms with x. 5x and 3x are both terms with x. N squared and 9n squared are both terms with n squared. When two terms are constants or have the same variable and exponent, we say they are like terms. And this is very important. So what does it mean to be like terms? It means that two terms are constants. So 7 and 4, because they're two terms that are constants, they can be called like terms or similar terms. 5x and 3x have the same variable. Notice it says and exponent. It doesn't just say they have the same variable, but that they have the same variable and exponent. So we see 5x and 3x. The exponent of the variable here would be 1. X is equal to x to the first power. And the variable, the exponent here of x would be 1. 3 times x is equal to 3 times x to the first power. So because they have the same variable and the same exponent, we can say that 5x and 3x are like terms. And lastly, x squared and 9x squared are like terms because they have the same variable, x, and the same exponent, squared. So if this was x to the third and 9x squared, we wouldn't say that they were like terms, but we could make them like terms. But anyway, let's learn the definition of like terms here. Terms that are either constants or have the same variables raised to the same powers are called like terms. Terms that are either constants, so they're both just unchanging numbers, or that have the same variables, the same letters representing numbers, And those letters, those variables, are raised to the same powers, that is, they have the same exponents. These are called like terms. So here we're given another list in this example here, and we're asked to find like terms. We've got y to the third, 7x squared, 14, 23, 4y to the third, 9x, and 5x squared. And as we look at this list, we can say y to the third and 4y to the third are like terms because these two terms have the same variable raised to the same exponent. Y to the third, and 4y to the third. We can also say that 7x squared and 5x squared are like terms because they both have the same variable, x, raised to the same power, to the square. We can say 14 and 23 are like terms because they're both constants. And then we're left with 9x. And there's nothing in this list that is like 9x. So 9x has no like term here. We read in the solution that y to the third and 4y to the third are like terms. We got that right. 7x squared and 5x squared are like terms. We got that right. 14 and 23 are like terms. We got that right. And there is no other term like 9x. We also got that right. So that solution is pretty easy. If you have any trouble, just go back and watch that section over again. Work on the exercises by yourself. And if you still need help, get in touch. I'm happy to help you. Let's move down to another example here. Identify the terms in each expression. Now we're given this expression here, and I've already given you the secret to identifying terms. I told you that terms are separated by addition and subtraction in expressions. So when we see 9x squared plus 7x plus 12, we have this expression. We're asked to identify the terms. So if I were to ask you how many terms are in this expression, you could look at it, and based on what I've told you, you can easily say there's 3 terms. 9x squared, 7x, and 12. 3 terms separated by addition. So it's very easy. But let's look back up to the definition of term and make sure we understand it as the book wants us to think about it. A term is a constant or the product of a constant and one or more variables. So when we look down here, we can see that 9x squared is the product of a constant and variables. So that's a term. We can see 7x is a product of a constant and a variable. So that's a term. And we can see that 12 is a constant. So that's also a term. So again, we have 3 terms. You can follow that definition as your guide, or you can just think about what I shared before. Again, in an expression, terms are those quantities or expressions separated by addition and subtraction. So we've got an addition here and an addition here, which divides 3 terms in this expression. Next, 8x plus 3y. Again, the guidance that I gave you is most simple. If we see expressions separated by addition or subtraction, those are terms. So 8x is a term and 3y is a term. The textbook here says that 8x is a term because it's a constant multiplied by a variable. And this 3y is also a term because it's a constant multiplied by a variable, 8x plus 3y. So there's 2 terms here, 3 terms here. And we see our answers are correct. The terms of 9x squared plus 7x plus 12 are 9x squared and 7x and 12. So 3 terms, as I said. And for 8x plus 3y, there are 2 terms, 8x and 3y, just as I said. So that's pretty simple, and you got some more exercises here if you want to test yourself. I recommend you do so, just to make sure everything feels easy to understand and simple to solve, okay? If there are like terms in an expression, you can simplify the expression by combining the like terms. So we just learned about like terms, And we're told now that when we're simplifying expressions, if there are like terms in an expression, we can simplify the expression by combining the like terms. So let's look at an example. 4x plus 7x plus x. So we have this expression. We've got three terms. 4x is one term, 7x is another term, x is a third term. Three terms in this expression. We notice that the variables are the same for all three terms. 4 times x, 7 times x, and x, or 1 times x. We also see that the exponents of those variables are all the same. So these are all like terms. 4x, 7x, and x are all like terms. So 4x plus 7x plus x, if we're asked to simplify this, we would just need to think about what we're actually being asked to do here. 4x means we're taking x 4 times. 7x means we're taking x 7 times, and x means we're taking x 1 time. So if we're taking x 4 times here, and we're taking x 4 times here, we're really taking x 11 times. And if we're taking x 1 more time here, well, then we're really taking x 12 times. And if we take x 12 times, that's equivalent to 12 times x. So 4x plus 7x plus x, or 1x, is equivalent to, or can be simplified to, 12x. So we're asked, how would you simplify? If you thought 12x, you would be right. And that's what we did. And here the textbook just illustrates what's going on here. 4 times x is taking x 4 times. 7 times x is taking x 7 times. And x is taking x 1 more time. So if we add 4 x's and 7 x's, we get 11 x's. And then 1 more would make 12 x's, or 12 times x, okay? So we can combine like terms and simplify the expression. So this was the original expression, and we simplified it to produce this simpler expression. Add the coefficients and keep the same variable. It doesn't matter what x is. If you have 4 of something, and add 7 more of the same thing, and then add 1 more of the same thing, the result will be 12 of those things. For example, if you have 4 oranges, where oranges is being used to replace x, if you have 4 oranges, and you add 7 more oranges, or 7x, and then you add 1 more orange, or x, you have 4 oranges plus 7 oranges makes 11 oranges, and then 1 more, which makes 12 oranges. So 4x plus 7x plus x, because these are all like terms, they can be combined, and this expression can be simplified to 12 times x, or x taken 12 times. So here in this example, we've got a little more complicated expression to look at. 2x squared plus 3x plus 7 plus x squared plus 4x plus 5. And we're asked to combine like terms. So the first thing we have to do when we're asked to combine like terms is to find the like terms. That's the first thing. We've got to figure out if there even are any like terms in the expression. And then if there are, we want to identify them so we can combine them. So we have 2x squared plus 3x plus 7 plus x squared plus 4x plus 5. So if we look for like terms, we're looking for terms that have the same variable and the same exponent. So here for 2x squared, we look down here and find another x squared, same variable, same exponent. So they're like terms. So 2x squared, or x squared taken 2 times, with x squared taken 1 more time is the same as x squared taken 3 times, or 3x squared. We then see 3x. We see the constant 3 multiplied by the variable x with an exponent of 1, which is not written. We see that's like 4x, which has the variable x taken one time. Or I should say the exponent is 1. So 3x and 4x are like terms, and we can combine them to make 7x. We then have 7, which is a constant, and 5, which is a constant. They can be combined because they're like terms since they're both constants, and that would produce 12. So we've got 3 times x squared plus 7 times x plus 12. And if we look down to the answer, we see 3 times x squared plus 7x plus 12, which is exactly what we came up with. So to combine the like terms, we combine 2x squared plus x squared, and we'd get 3x squared. And then we would combine plus 3x and plus 4x to get plus 7x. And then we'd combine plus 7 and plus 5 to get plus 12. And that would be the solution to this problem. We've simplified this complicated, messy expression by combining like terms and producing a much simpler expression. That's the goal. So you've got some more examples there you can work with. This is really just like a puzzle. It's really quite easy. Most people don't like algebra because they simply don't learn the principles, and then they get stuck in higher level algebra classes that they're really not prepared for. If you learn all the details one step at a time, it's really just like solving puzzles. It's very simple. So here in the box, we've got an explanation of the rule for combining like terms, how to combine like terms. First, identify any like terms in the expression. Then you can rearrange the expression so the like terms are together. And then lastly, you can add or subtract the coefficients, that is the constants or the numbers in front of the variables. You can simply add or subtract them and keep the same variable for each group of like terms. So there's your rule simplified for you that you can apply. You should study this rule and then go and use it to simplify these complicated expressions. Just follow these directions and see how they help you to solve that problem there. Okay? The next section, translating an English phrase into an algebraic expression. Translating an English phrase into an algebraic expression. Now we're already an hour and 12 minutes into this video, so let's just see how long this last part is. It's a little lengthy, so what I think we're going to do here is I think we're going to stop this video here. We'll stop right here before this section on translating an English phrase into an algebraic expression. So we have time to read through that and make sure we learn it carefully. So the good news is we've got over another hour of instructional time for elementary algebra. Again, you need 120 hours of instructional time to be able to say that you've completed one high school year of algebra. So that's what we're going to work towards. And this is another hour plus of instructional time. So you've now got at least 3 hours. If you've watched the 3 videos so far in elementary algebra, you're probably over 3 hours already, which is great. And we're just going to keep working through algebra like this so that you can learn algebra by reading and studying the textbook carefully. And you can also satisfy the time requirements for a high school algebra course. So I hope you found this guide helpful. I hope you find that just having me sort of push you along or pull you along sometimes is helpful to get through the content. I hope that you're able to pay attention, to read along with me, see what I'm doing, and I hope that you use your ability to control the video, to hit pause, to back up, to watch things over again, and make good use of this resource. The time that you spent working with these resources can all be counted as instructional time, so it's good for you to get as much time as you can working with these videos, watching these videos, and so on. That's the reason why I'm making them. So I hope you find this helpful. If there's anything in the lesson that we've gone over together that you just don't feel comfortable with, or you feel you'd like some more explanation, or there's a problem that you don't feel like you can solve correctly, let me know. I'd be happy to help you. You can either post on the course page or you can send me an email, whatever is easier for you, and we'll work through it together. And I'll make sure that you understand what you need to understand so you can move on in elementary algebra. I hope that's helpful. God bless your studies.